In this section, we're going to talk about two topics that relate to using a tangent line as an approximation to the curve represented by the function itself. One is called linear approximations, and the other is the concept of differentials. The first topic in this section is linear approximations, and this is based on a concept that we've discussed before. And that is, if you have a graph of your function, say here, this blue curve is the graph of f of x, and you pick a point, this point has x coordinate a, right? And you create the tangent line at that point, that as long as you stay near this point, the tangent line is almost the same as the graph of f in blue. And the more you zoom in towards this point, the more the green curve or the blue curve and the red line look the same. So that's our whole concept here, is that as long as you stay near the point where it's tangent, the tangent line is actually an approximation to the graph of f itself. So one reason why you might want to use the tangent line as an approximation to the curve itself is, suppose you're asked to evaluate f at some decimal number like 3.258. That could be hard to calculate by hand, right? Especially if f has a complicated formula. To plug in a number like that everywhere you see x, especially if you've got x raised to powers, right? That could get very complicated. So it might be easy if so let's say your number is 3.25, then that's the nearest integer would be 3. So you might choose your x coordinate 3 as your point and make your tangent there. So then, like I said, plugging 3.25 into your function might be a lot of work. But if you can find the equation of this tangent line, linear functions always have a very simple formula, right? Y equals a constant times x plus a constant. So it would be pretty easy to plug 3.25 into L of x and calculate that by hand. And as long as the 3.25 is pretty close to the point 3 where we made it tangent, then that's using L as an approximation to f will be pretty good as long as you stay close to the point where it's tangent. So this gives us some motivation for why we might want to use the tangent line to approximate the curve f. Here we're going to find the equation of one of these linear approximations. Now remember, the linear approximation is just the tangent line, so it's a concept we've discussed before. We're just giving it a new name at this point. So we've actually already done this, so I've just rewritten the formula here. If we're making the tangent at the point where x is equal to a, so this would be the ordered pair for the point where it's tangent, then the equation of the tangent line, we've derived this earlier using the point slope form. Remember, the slope is given by the derivative, and you have to plug in the x value of your point into the derivative. So f prime of a, that's the slope. And so we had y minus the y coordinate of your point equals the slope times x minus the x coordinate of your point, and then we solved it for y by adding f of a over to the right side. So we've done this derivation before. This is the equation of the tangent line in red here. Now we're just going to call it L of x. We're going to name this function by replacing y with L of x. And we give it that name because we call it the linearization of f at a. Right? And the reason we call it linearization should be pretty clear. We're approximating f, which is a curve, with a linear function, which is the tangent line, at the given point. And so again, the idea that we've been discussing is that L of x is approximately equal to f of x, right? The wavy equal sign means they're approximately equal. which means f of x is approximately equal to the formula for L of x. So last thing to mention here is I wanted to emphasize again, the approximation is good as long as you stay near the point where it's tangent. If you want to look at an x value far away from a, maybe way over here, and use L of x to approximate f of x, it's not such a good approximation anymore, right? These curves are no longer very close together if you get far away from this point. We're asked to find a linearization of the given function, square root of x plus 3, at the point where a, which is the x coordinate, is equal to 1. And then we're going to use it to make two approximations, the square root of 3.98 and the square root of 4.05. Let's start by finding the linearization. So up at the top, you can see I've copied the formula we just derived for the linearization that we're calling L of x. And you can see there's two things we need to compute in order to plug into this function. Since a is equal to 1, we're going to need f of 1 and f prime of 1. So that's what we're working on first. Just make a note here. We need to find f of 1 and f prime of 1. So f of 1 is pretty easy. They didn't even show the work here, right? So f of 1, just to show that, would be the square root of 1 plus 3, just plugging into the formula for f of x, which is the square root of 4, which is 2. So that explains where this came from. Now let's back up here. To find f prime of 1, we first need a formula for f prime of x. So we start with our formula for f that was given, and we compute its derivative. So this is a composite function, right? If it were just x to the 1/2, it would be a power function, but we've replaced x with some inside part. So the inside part is x plus 3, the outside function is x to the 1/2, right? Or u to the 1/2. So using the power rule, for the outer function, you bring the 1/2 down in front, keep the inside part the same, reduce the power by 1. 1/2 minus 1 is negative 1/2. Then you have the second factor of the chain rule. We need to multiply by the derivative of the inside part. Well, the derivative of x plus 3 is 1 plus 0, which is just 1. So we multiply by 1, which you don't even have to write. So here's f prime. And then we could simplify it. We know the negative in the exponent means you can move it to the denominator and make the power positive 1/2. And a power positive 1/2 is the same as a square root. So here's our simplified f prime of x. Now what we needed was f prime of 1. So when we plug 1 into here, we get 1 over 2 times the square root of 1 plus 3. So that square root is just square root of 4. Square root of 4 is 2. Multiplying by the other 2 in front of it, we get 1/4. So that explains where this came from. So now that we know the values that we go here and here, we're ready to write our formula for L of x. So we'll do that next. So now we're going to write our formula for L of x. So the first thing is we were given that the value of a is 1, right? A is representing the x coordinate where we're making the tangent point. And so first we plug in 1 for a in these 3 spots, and it looks like this. Then we can use what we calculated on the previous slide, and that was that f of 1 equals 2, and f prime of 1 equals 1/4. So we just made those substitutions. And then you can simplify by distributing the 1/4, and then you can combine the two constant terms, which would be 2 minus 1/4, which becomes 7/4. And then here's the 1/4 times x written as x over 4. So we just determined our formula for L of x. is 7/4 plus x over 4. And so remember, what we're using L for is to approximate the given function. So here was the formula for the original f of x. And then over here, we have the formula we just found for L of x. And notice we're saying they're approximately equal, but only if you stay near the point where it's tangent, which means the x-coordinate needs to be near the value 1. We've completed the first part of the example, which is to find the linear approximation. Next, we wanted to use our linear approximation to estimate the values of these two square roots. Now, how does that relate? Well, remember, this is what we concluded at the end of the last slide. This is the f of x, and we're saying it's approximately equal to our L of x. Notice the f of x is the square root of something, which corresponds to what we're seeing here. So if we want the square root of 3.98, and we want to think of it in terms of this function, x would have to be 0.98, so that we would have under the square root, we would have this 3.98. So we're going to choose x to be 0.98, and that means f of x, or I should say f of 0.98, just using the definition of f of x, right, which is this formula here. F of 0.98 would be the square root of 0.98 plus 3, which is exactly what we're looking for, square root of 3.98. So the important thing we had to realize here is that this value we were asked to compute, the square root of 3.98, can be related to the function f. Right? And then you had to figure out what x value do you need to plug into f to arrive at this expression here. So we determine that x value is 0.98. So then this is hard to calculate by hand, right? The square root of a number like that is not obvious. We know it's a little bit less than 2, right? Because the square root of 4 is 2, and this is a little bit less than 4. But we want to get a better approximation than just say it's a little less than 2. So here we're approximating this expression, the f of x, with this linear expression. So we're going to plug in the same x value into the right side. Okay, so that'll be 7/4 plus 0.98 over 4. Okay, so just to label again more clearly, this expression is f evaluated at 0.98. On the right, this is L evaluated at 0.98. And we've said that L and F are approximately equal as long as you're plugging in numbers that are near 1, right? And 0.98 is definitely near 1. So this, it's not the easiest thing in the world to do by hand, but it's a lot easier than this square root. Right, so you could calculate this by hand and get 1.995, and notice it's just like we expected, it's a little bit less than 2. So now we've approximated the square root of 3.98 by using our linear approximation. Now we want to do the same process to approximate the value of the square root of 4.05. Right, if you just think about this, we know it's going to be a little bit bigger than 2, but we want a better approximation than that. So the next question is what we want to relate it to this function. What would x have to be so that x plus 3 becomes 4.05? Well, 3 plus what will give you 4.05? The x would have to be 1.05. So in this one, we're going to choose x to be 1.05. And notice that f of 1.05, just using the formula for f, is the square root of 1.05 plus 3, which simplifies exactly to what we're looking for, square root of 4.05. So this is the x value we're plugging in. So this expression here could be represented as f evaluated at 1.05. And on the right, we're going to take L and plug in the same x value. And then we know these two should be approximately equal because notice the x we're plugging in is near 1, right? Which is the requirement in order for the approximation to be very good. And then you could calculate this by hand, and it comes to 2.0125, which was just what we expected, a little bit bigger than 2. So looking at the picture, just to relate what we did here to our graph. So here is, in blue, is the graph of the given function, square root of x plus 3. And remember, we were given a equal to 1. So here's 1 on our x-axis. Move vertically, there's the corresponding point on the curve. The y value would be found by plugging 1 in for x here. You get square root of 4, which is 2. So that's the point 1, 2. We've sketched the tangent line, and we can label the equation of that line because we found that earlier. Now let's relate this picture to these two values we computed. So the square root of 3.98 was found by choosing x equal to 0.98. So just to the left of 1. And if you move up vertically, that would put you around here. So the actual value of the square root of 3.98 would be the y value on the blue curve right at this point. And the approximate value we used, instead of going, we'd use the same x value, but instead of going to the blue curve, we'd go to the red line. But notice they're really indistinguishable. They're so close at this location that there's not much difference between the two. So that gives us some credibility that this approximation is probably pretty good. Now for this second approximation, for the square root of 4.05, we used an x value of 1.05, which is just barely to the right of 1. And we could make the same analysis there. Right? So f of 1.05 is the value we're looking for. And that's represented by, if you move vertically above this location, it's the y-coordinate where you hit the blue curve. But what we actually used as our approximation was not that, it was the y value when you hit the red line. But again, the blue and the red are so close to each other that we can rely on our approximation as being pretty good, pretty close to the actual value. Then there was one other question about whether our estimates were too big or too small. Were they overestimates or underestimates? And you can see that by looking at the picture, right? In this case, the tangent line lies above the curve. So the y values we used as our approximations were just slightly above the actual values, which are on the blue curve. So we can say our approximations are overestimates, although it looks like they're not very far over. They're pretty close to the actual values. And you can check by putting these in your calculator and seeing how closely it agrees with the values we found here. Here we're just doing some further analysis of the example we were just looking at. So we've created a table where we did some estimates of various square roots. Notice the two that we did are on here, right? The square root of 3.98, we did that one, and we did the square root of 4.05. Then there's others on here that we could get using the same process. So let's look at this one we already did. We used an x value of 0.98, if you recall how we did this one. And then this was the approximation we got by plugging this x-coordinate into our function L of x. The actual value is we kind of had to round off because the decimal continues, but we wrote more decimals, right? If you were to plug 0.98 into f of x instead of L of x, you would get this. And so you can see how close our approximation was. We just didn't have as many digits, basically. And then we did this one also with an x value of 1.05, and this is when we plugged that into L, we got this value. Compare that to the actual value if we had plugged into f of x instead of L of x. So then we've created a table where we did this for lots of different square roots, and in each case we put the corresponding x value that you would have to plug in to f to create this expression. So what I want to look at is the comparison of our approximation and the actual value. So plugging into L versus plugging into f, right? So this column is f of x. So if you look and compare these two, they're pretty good. These are good. These are perfect. Why is that one perfect? Well, this square root of 4 is associated with an x value of 1, right? Because it's the square root of 1 plus 3. And notice when we plug 1 into L and we plug 1 into f, they're the same. That's because 1 is the point, x value 1 was the point where it was tangent. And if you recall the graph, the tangent point is the same on both f and L because they touch each other there, they intersect there. So that will always be the case, that the L and f will be equal at the point where it's tangent. Still pretty good here, but then notice these aren't so great. For the square root of 5, our approximation was not so close to the actual value. And for square root of 6, even a little bit worse. So why are they getting worse? Well, notice the x values we used. These are getting significantly farther away from 1. And we've emphasized over and over, our L is a good approximation to f only if your x value is close to the x value where it's tangent, which in this case was 1. And so we're seeing that the accuracy deteriorates the farther away from 1 your x coordinate gets. We're asked to approximate the value of e to the power 1.04. Right, that would obviously be difficult to calculate by hand. So let's think about using a linear approximation. So we need to start by let me say this, use L of x to approximate. What function do we want to approximate? Well, notice we have e to some power, so we could define our function to be e to the x. And then we need to say where we want to make our L of x tangent. So we just give the x coordinate where we want it tangent. And so we want to choose a value that's easy to work with, usually an integer, but is near the point that's given here, this 1.04. So the obvious choice here would be to use 1 for a. Okay, so let's start by recalling our formula for L of x. So it's f of a plus f prime of a multiplied by x minus a. And we chose to use 1 for a, so now I can rewrite L of x substituting in 1. So we have f of 1 plus f prime of 1 times x minus 1. So there's two pieces that we need in order to substitute in here, f of 1 and f prime of 1. Let's calculate f of 1 first. So just look at your formula for f of x, which is e to the x. We plug in 1 for x, so we get e to the 1, which is e. Now to find f prime of 1, there's a first step. First you have to find f prime of x. Once we have that, we can plug in 1. So to get f prime of x, we look at our formula for f of x, which is e to the x, and we take the derivative, which we know is just the same, e to the x. Now that we have that, we plug 1 in for x to get f prime of 1. So that's e to the 1, which is e. So now I'm going to rewrite my formula for L of x, and I'm going to make those two substitutions. So f of 1 was equal to e, and then I have plus f prime of 1 is also equal to e, and then multiplied by x minus 1. And then if we wanted to simplify, we could distribute the e over the parentheses. And notice the e and the minus e cancel, we get e times x. So now we have our formula for L of x equals e, which is a constant, times x. Okay, now let's use it to approximate what we're looking for. So e to the 1.04. We want to view this as f of some number. And we chose f to make this easy, right? E to the 1.04 just means x needs to be 1.04. In other words, it's the same as f evaluated at 1.04. Okay, but then we're using L to approximate f, so this will be approximately equal to L evaluated at 1.04. And then to find L of 1.04, you just plug 1.04 into the formula for L. So it will be e times 1.04. I'm going to flip the order, 1.04 times e. So then if you remember the first few digits of e, we can then take this further to get a decimal for this. So this would be 1.04 times, so the first few digits of e, we have 2.71828. And then you could calculate that by hand if you had the time, or you could go ahead and use your calculator. And this comes to our approximation for e to the 1.04 to be 2.827. That's probably far enough. And then just for comparison, let's see what the calculator gives us for e to the 1.04. So when I put this in, I'll round it off to the same number, or maybe a few more digits. We get 2.82922. Okay, so you can see ours is fairly close. They agreed out to the hundredths place, and then we were off once we got to the thousandths place. So in this example, we had a lot of freedom, right? Just said approximate. It didn't say how to do it, but we now know this linear approximation is a good way to deal with problems like this. Takes something that would be hard to calculate by hand and gives us a way to do it, to approximate that in a way that's much easier to do by hand. These linear approximations have applications that are really widely used in physics. So if any of you take physics in the future, you'll almost certainly see one or both of these approximations that I'm about to review. So the idea is, if you have a function that's maybe a little challenging to evaluate, just like we saw in our previous examples, you can replace the function with its linear approximation. So a common example is the trig function, sine theta, for example. That appears in lots of places in physics, and one place it appears is the formula for the period of a pendulum. So rather than continuing to use sine theta, they replace it with its linear approximation, which turns out to be L of theta equals theta. So in physics, it's very common to see sine theta replaced with theta, and I should mention that it's the linear approximation if it's tangent at x value 0 or theta value 0. So sine theta is close to theta, but only if theta is near 0. So you can actually verify this linearization by defining your f of x to be the sine of x function. We're choosing it to be tangent at x value 0. And if you calculate L of x using the methods we've been using, you'll get L of x equals x, which means sine of x is close to x, but only if x is near the point 0 where the tangent is. So this is what is very common in physics, is to replace sine of x with x, but only if you know x is near 0. Another example in physics is in optics, and there's a case where you have light rays arriving at shallow angles relative to the optical axis. So shallow angles means they're small, they're near 0. So near 0 degrees. So then in this work, both the sine function and cosine functions appear. And so what we do is we find the linear approximations to those two functions where we make the tangent point at x coordinate 0 or theta coordinate 0. We already discussed for sine that sine of theta is approximately theta for theta near 0. You can do the same thing with cosine. Find the linear approximation to the cosine function at x value 0, and you'll get it's equal to 1. So as long as theta is near 0, cosine theta is near 1, and sine theta is near theta. So in these physics applications, they'll often replace sine theta with theta and replace cosine theta with 1. The second topic in this section is differentials. So I want to first introduce the concept, and differentials is really just a different way of framing the idea of a linear approximation. But they're very useful, especially if you get to calculus 3 in physics. The differential concept is very useful. So we start off with the function f of x, and we define the two differentials. One is for x, we call it dx, and the other is for y, we call it dy. So let's start with the differential dx. We're going to consider it an independent variable, which means you can choose whatever number you want for dx. Once you choose dx, it determines what dy will be. So dy is dependent, a dependent variable, because it depends on your choice of dx. Now here's how we define dy. So you take your given function f, you calculate its derivative, and then you multiply it by the differential dx. Now we'll explain why it's defined this way as we go through this the rest of the section. So you can see here y not only, or dy depends not only on x or dx, but it also depends on x because the x is plugged into f prime. Okay, so if you choose a value for dx and you choose a value for x, we plug these into this formula and it gives us a value for dy. Here I'm going to use a graph to explain the concept of differentials. So we use two notations, delta and d. So when we say delta x, you've seen this before, it just means change in x. And when you see delta y, it means change in y. So it implies that we're moving from one point to another point. So in the graph, we've sketched our function in blue. This is our f of x. And we've picked an x-coordinate and labeled it x. And we find the corresponding point on the curve. We're going to put a tangent line at that point. And then, just like we were discussing earlier in this section, as long as we stay near this x-coordinate, the tangent line is pretty close approximation to the curve itself. So now we're going to consider changing x. So we're going to move to either the right side or the left side of x. In this picture we move to the right a little bit, and the amount that we move would be the change in x, right? So the distance from the original x value to the new x value, that distance covered, that's the change in x. We're going to define the differential dx to be exactly the same as delta x. Okay, so that's just a definition. So the differential dx is easy to deal with. It's just defined to be the same as delta x. Delta y is the one that requires a little more thought. So in our picture, we've moved from here on the x-axis over to here. Each of those points has a corresponding point on the curve. And so the y values changed as a result, or sorry, I should be looking at the curve, not the tangent line. Right? So as a result of changing x, the y value changed. Right? We moved from point P to point Q, so those have different y coordinates. So we can indicate how much y changed by looking at the distance between the two y coordinates. So here's the y coordinate for P, and then here's the y coordinate for Q. This vertical distance that we've labeled delta y represents the change in y, which is why we've called it delta y. Now here's where the tangent line comes in. And that's because delta y could be hard to calculate because f of x might be a complicated formula. So instead of using f of x, we're going to use the L of x, the tangent line. And we're going to go to our new x coordinate, which is x plus how much we changed on the x direction. And instead of measuring using this point on the curve, which could be hard to find, we're going to take this x coordinate and plug it in to L of x, which will be much easier to find. So now we have point R instead of the real value, point Q. So our new y value will be estimated by the y value at point R, whereas the actual value is the y coordinate of point Q. So then our dy is not going to be the same as delta y. Dy is the difference between the original y coordinate and the new y coordinate. The difference is we're using the y coordinate on the tangent line instead of on the curve itself. Okay, so in our picture, just to make a note here, delta y is uses the actual curve, but dy uses the linear approximation, the tangent line. Right, so here, that's our L of x, the pink line or the red line. Okay, so again, the idea is dy is an approximation to delta y, where we've used the tangent line in place of f of x to calculate how much the y value moved when we changed from one x coordinate to another. So what we're going to see in the next slide is we're going to argue that the formula I gave you for dy on the previous slide is exactly what we've labeled here as dy. Now I'm going to present the argument that the dy that we've labeled here, as I just described it, is actually the same as the way we defined dy a couple slides back, which was this formula. We defined dy to be f prime of x times dx. Okay, so here's the argument. So we start with point P having x coordinate x, which means the y coordinate would be f of x. So that point would be, if this is x on the x-axis, point P would be directly above that on our curve of f. Then we move, in this case to the right, a distance delta x, and we find the corresponding point on the function, the blue curve. So that would be x coordinate is now x plus delta x, which means the y coordinate would be f evaluated at that x value, x plus delta x. So point Q is right here. And then just like I discussed earlier, we define dx to be the same as delta x. So that is the distance between the starting x coordinate and the new x coordinate. So then the delta y represents how much the function value changed. In other words, how much did the y coordinates change when we move from one x coordinate to the other. So in moving from point P to point Q, this distance here is how much the y coordinates changed. And we can calculate that by taking the y coordinate of the new point Q and subtracting the y coordinate of the point P. And so we take this y coordinate minus this y coordinate, and that looks like this. So delta y again is the exact change in these function values when you move from this x value to this other x value. Now we're going to consider the tangent line. So we know for sure that the slope of that tangent line is represented by f prime of x, right? Because x is the point where it's tangent. Now this next statement here needs a little explanation. So we know that the slope of this line can be also calculated by rise over run. The rise is this length here, right? Because here's our run and our rise. So let me write out slope equals rise over run. And if you solve this for rise, because the rise is what we're trying to find, right? We're trying to find what this length is. We're calling it dy, but we want to prove that it really equals the dy as we defined it. So I'm going to take what I just wrote and solve it for rise. So I get rise equals slope times run. But the slope, we just said, is f prime of x. And the run we can see in the picture is, you could either call it dx or delta x. We're going to use dx. And that's exactly what we defined. That's the definition of the differential dy. Okay, so that's just the explanation for this, the distance from S to R, right, which is this piece here. Now it says directed distance. That means it could be positive or negative. Usually distances are always positive. But here a directed distance would tell us that if it turned out to be a negative number, it just means that the y values decreased as we moved from the first x coordinate to the second x coordinate. But we've achieved our goal. We proved that the dy, as I described it here, right, the change in the y coordinate where we use the original point and then the new point on the tangent line rather than using the function itself, we're calling that dy. That distance is measured exactly by this formula, which is the definition of dy. And then down at the bottom, this is just summarizing what I've been saying. If we change x from an original point x and we move it to the right dx units to get to our new point, we want to discuss the resulting change in the y coordinates as you move from one point to the other. Jump down here. Delta y is the exact change in the function. So the y coordinate here to the y coordinate here, it's the difference between those two. Whereas dy is the approximate change, and it's approximate because it's how much change is in the tangent. So it uses the tangent instead of the curve and measures that distance. So again, dy is used as an approximation for delta y because the dy is usually easier to calculate. We're asked to find the differential of the given function y equals sine of pi x over 2, and then evaluate dy, which is the differential of y, at a given value of x and dx. So let's start by calculating the differential. So remember our formula for dy is just f prime of x times dx. So what is f of x? Well, it's the given function, right? So here the f of x they're talking about is this sine function. So we need f prime so we can plug that into the formula. So just use derivative rules here to find f prime. So this is a composite function because it's got, instead of just plain sine x, it's sine of something else. So we start with the derivative of the outer function, which is the sine function. Derivative of sine is cosine, but then you keep the inside part as it is. And then you multiply by the derivative of the inside part. So the inside part could be viewed as a constant pi over 2 times x. And the derivative of a constant times x is just that constant. So it's just pi over 2, and I'm going to put that in front. So now we just plug that in to our formula for dy. So dy equals, plug in for f prime of x, and then after that we have dx, right? So I just plugged in here, and then off to the right it's multiplied by dx. So that was the first part, was to find the differential, and that's all there is to it. It's pretty simple actually, if you know what they're asking for. Now the second part says evaluate it at a given x value and dx value. So that just means plug those into our formula. So dy equals pi over 2 times cosine of, now plug in 2 for x. So the numerator will be 2 pi, denominator 2, and then plug in for dx, negative 0.1. Now let's simplify. So inside the parentheses of cosine, the 2's cancel, so it's cosine of pi. And then, just to separate this, then we multiply by negative 0.1. Now cosine of pi is negative 1. So we get pi over 2 times negative 1 times negative 0.1. The two negatives become positive, so we have pi over 2 times 0.1. You could leave it like that, but maybe to look a little nicer, we could write 0.1 as 1/10. So we have pi over 2 times 1/10, and then that could be written as pi over 20. So actually working with the formulas here is pretty simple, right? The formula for dy, you just have to know what your f of x is and calculate its derivative and just substitute that in. And then you can be asked to do various things with that formula. So in this case, they just gave us the values to plug in for x and dx, and then we simplified and got our final answer to be this number, pi over 20. So in this example, we're given a function here, it's its formula, and we're told that x changes in part A from 2 to 2.05, and then in B we'll do a different change from 2 to 2.01. And in each case we're going to calculate two things, delta y and dy, right? So delta y is the exact change of y based on the function formula, and dy, the differential, is the amount that the tangent line changes. So let's start with part A. And let's find delta y first. So delta y is just the ending y value minus the beginning y value. Right, and since we're going from 2 to 2.05, the ending y value is f of 2.05, and the beginning y value is f at the beginning x value, right, f of 2. So up here we're calculating those two things, and that's just a matter of plugging the given x value into this formula. So f of 2, we get 2 cubed plus 2 squared minus 2 times 2 plus 1, simplifies to 9. And then we need f of 2.05, so this time we plug 2.05 into the same formula, simplifies to this decimal here. So now we know these two values, we plug them in, right? This long decimal minus 9, which gives you 0.717625. So this would be a little hard to calculate by hand because of these numbers here, having to cube 2.05 and then square 2.05, etc. But that's the exact amount that the function value changed when we moved from x value 2 to x value 2.05. Now on the right, we're going to calculate the differential dy. So we start with the formula for dy, which is just f prime of x dx. And all we need to do is look at our formula for f and calculate the derivative. So just using the power rule, we get 3x squared plus 2x minus 2 plus 0. Substitute that in. So now we have our formula for dy in general. Now we need to plug in the specific information. So we're starting at x value 2. So we're going to let x equal 2. And then we're moving to the right by 0.05. So the delta x is 0.05. And remember, delta x and dx are the same. So dx is also 0.05. So now we have a number for x and a number for dx to plug in to our formula for dy. So we replace these two x's with the number 2, and we replace this dx with 0.05, and it looks like this. Now this would be much easier to calculate by hand, right? So doing that gives you 0.7. So we look at the two values we computed. The dy was 0.7, the delta y was this longer decimal that starts with 0.7. Those are supposed to be approximately the same, and you can see they are very close. And again, the point I keep emphasizing is the dy is much easier to calculate, and it can be used for an approximation of the exact change in the function. So now we'll go through a similar process to answer part B. Part B is just using a different incremental change in x. So we're starting at the same x value of 2, but this time we're only going over to 2.01 for the new x coordinate. So we'll start with the delta y. So just the definition would be f at the ending x value minus f at the beginning x value. We've already calculated f2, right? Just mention here f of 2 is equal to 9. And then we need to find f of 2.01, so just plug this into the formula for f, simplifies to this decimal here. And then we subtract, right? We do the value we found for these two things, we subtract them, and we get 0.140701. Now over to the right, we're going to find dy, the differential. This part's exactly the same as in part A, it's just the general formula we found for dy by substituting in our f prime of x. This time the dx is different, right? The x is still 2 because we're still starting at the original x value of 2. And then the distance we moved was 0.01 to get to the new point. And by the way, we use, if it moves to the right, you use it as a positive distance. If the new point had been to the left of 2, we would have used a negative value for dx. Okay, so we're still using an x value of 2, and we have a new value for dx that's 0.01. So into our formula here, we're going to replace these two x's with 2, which you can see there. And then we replace this dx with 0.01. Simplifying this, which again would be fairly straightforward to do by hand, we get 0.14. And again, we can compare the value we got for dy with the value we found for delta y. Again, they're approximately equal, which they should be. This example will illustrate a common application of differentials. And that is if you're measuring something and you know your instrument that you're using to take the measurement has a certain error to it, a maximum possible error, you can use that in an instance like this one. So here we have a sphere, and we use our measuring tool to measure the radius of that sphere. And we found 21 centimeters to be the radius. But we know that our tool has an error of at most 0.05 centimeters. So we could be off by at most 0.05 centimeters in either direction. Now if you calculated the volume based on the measured radius, there's going to be a possible error in the volume because of the possible error in the radius. So the question is, what's the maximum error in your calculation of the volume that results from the possible error in measuring the radius? Okay, so this is the type of problem where differentials can be used, because think about what differentials are doing. We have a function y equals f of x. If x changes by a little bit, the differential tells us how much y changes. And that's exactly what is happening in this situation. So we need a function to work with in this problem. And since they're talking about volume and radius, the obvious formula is the formula for the volume of a sphere of radius r. So that's a well-known formula, which we've written here. Volume is 4/3 pi r cubed. So the radius is known to have a certain error, maximum error. We'll call that error the change in the radius from its true radius measurement to the value that we measured for the radius, which will be a little bit different because of the error. So that error will be the distance between the true measurement and the actual measurement. And that's represented by dr, which is the same as delta r. Now we want to find the corresponding error in the volume. The exact change in the volume is delta v, but we approximate it with the differential dv. So remember the general formula for the differential is dv equals f prime of r times dr. The f of r is the formula we're dealing with, which is this volume formula. So f of r is 4/3 pi r cubed. So then, looking at that formula, we calculate its derivative, f prime of r. So the 4/3 pi is all constant, so that gets carried along. And then we use the power rule to find the derivative of r cubed. So you bring the 3 down, cancels with this 3 in the denominator. So now we have 4 pi out in front. And then we've reduced the power by 1, becomes r squared. So f prime of r is 4 pi r squared. And so you can see that's been substituted in here for the f prime of r, and then we have the dr multiplied to the right. So now we have our formula for the differential dv. Now we have to plug in the known values for r and dr. So we just discussed the dr up here is how far r is off from the true measurement, and the maximum that it's off was given to be 0.05 centimeters. So we're going to let dr be 0.05. Now r will be the measured value, right? We don't know the exact value, we only know the measured value. So r will be 21 centimeters. So we just plug those numbers in here. So we'll have 4 pi times 21 squared times 0.05. Putting that in a calculator, we get 277. Now that's the, because we use the maximum error when we set our dr as 0.05, the maximum error in the radius will give us the maximum error in the volume. So this 277 is the maximum error in the volume. We just need to put units on it. And since the radius was measured in centimeters, that means the volume would be cubic centimeters. So that's kind of amazing that the volume would be off by that much, right? The radius measurement was off only by this small amount, 0.05 centimeters. But by using that measured value with that possible error to calculate volume, the number you calculate from volume, which we didn't do here, but if you did calculate the volume using that radius, the value you compute could be off by at most 277 cubic centimeters, quite a large amount. So it's kind of an interesting example to see how differentials can help us understand errors better. We were just saying how the maximum error in the volume appeared to be very large compared to the error in the radius. But to get a better feel for this, it actually makes more sense to look at what we call relative error rather than the exact or the distance type error. So relative error is defined by taking the actual change in something, in this case volume, and dividing it by the total volume. So to calculate that for this example, first we'll estimate delta V with dV, and then we can plug in for dV this formula that we found earlier by taking the derivative of the volume function. And then plugging in for, I shouldn't say, it was the derivative of the volume function times dr, right? It's the differential formula. And then the volume formula here. And then simplifying, we can cancel the 4's, cancel the pi's, cancel r squared. This 3 flips up to the numerator. And after all that's canceled, we get 3 times dr over r. Now this dr over r is exactly the same idea of relative error, but for radius instead of volume. Right? dv over v is relative error for volume, so dr over r is the relative area for radius. So making that observation, we have this conclusion written over here. The relative error in volume is approximately, right, 3 times the relative error in the radius. Now we'll actually calculate the values of these two relative errors. So we'll start with the relative error for radius. So that's defined as dr over r. So recall in this problem, we were told that the tool we were using to measure the radius had a maximum error of 0.05 centimeters. So that's the dr. And then the r was the measured radius using that measurement tool, which was 21 centimeters. And simplifying this fraction, we get 0.0024, and that would be a unitless number because over here the numerator and denominator were both in centimeters, so the units cancel. And then to calculate the relative error in volume, using this formula that we derived on the previous slide, we just take 3 times the relative error in radius, which is this number. So just to clarify where this 0.007 came from, that was 3 times 0.0024, which is, so now we have the relative error in volume is only 0.007. And these are the decimal forms of the error, but these could be expressed in percentages, right, in the usual way. To convert a decimal into percentage form is to move the decimal place right 2 points and then put the percent sign. So for radius, the relative error is 0.24%, and then for volume, we get the relative error is 0.7%. Moving on to section 311, which is on hyperbolic functions. So these are a new class of functions, and we'll learn their definitions, that appear widely in some of the applications of mathematics. So they may be useful to you if you're in the sciences. You may come across these functions in the future. So we want to make sure you're familiar with these functions and their derivatives. So it turns out there are certain combinations of the two exponential functions here, e to the x and e to the negative x. And by combinations, we mean like constant multiples, sums, and so on. We'll see these formulas in just on the next slide. But these particular combinations appear frequently in math and especially in applied math. And these functions, these combinations, have a lot of analogies to the trig functions. Even though they're not defined using trig functions, they're defined with exponential functions. And we all know there's a connection with the trig functions to the unit circle. And it turns out that these functions we're considering here, that we're going to call the hyperbolic functions, they have a similar relationship to a hyperbola. And that's why they have the name hyperbolic functions. And because they have the similarity to the trig functions, but with a hyperbola association, all of the functions are named hyperbolic followed by a trig function name. For example, hyperbolic sine, hyperbolic cosine, and so on. So here we present the definitions of the 6 hyperbolic functions. Notice the names of them first before we look at the formulas. SINH. So the H stands for hyperbolic. The SIN, of course, sine. So the way we read that notation is hyperbolic sine. And then it's similar for all the others, right? The one below it is hyperbolic cosine, hyperbolic tangent, hyperbolic cosecant, hyperbolic secant, and hyperbolic cotangent. Now let's look at the definitions. Notice the formula for hyperbolic sine. Just like we said on the previous slide, it's a particular combination of e to the x and e to the negative x. So it's e to the x minus e to the negative x, and then the whole thing is divided by 2. Now the formula for hyperbolic cosine, almost the same except it's a plus instead of a minus. Now all the others are defined in terms of hyperbolic sine and cosine. And their definitions follow the familiar identities that we know from trigonometry, right? For example, we know in trig that plane tangent is equal to sine over cosine. Here, the same relationship holds, but they're all hyperbolic, right? So hyperbolic tangent of x is hyperbolic sine over hyperbolic cosine, and then you could refer back to those formulas and substitute them in and see how hyperbolic tangent is just a combination of e to the x and e to the negative x. Same thing with all the others, right? They use the familiar trig identities for these others, but all hyperbolic versions of those functions. Based on the definitions of those 6 hyperbolic trig functions, we can arrive at some identities. So we're not going to prove these, but what I want to notice is, or point out, is that these are very similar. Some are almost the same, exactly the same, and some are just similar to identities from the regular trig functions. So for example, this first one, let's look at the cosine version first. Hyperbolic cosine of negative x equals hyperbolic cosine of x. In other words, that negative sign doesn't make a difference. That is also true for the cosine function. If this were plain cosine, we have the same identity. For hyperbolic sine, it's slightly different. If you have hyperbolic sine of negative x, if you want to drop the negative on the inside, you have to also multiply by a negative in front. The regular sine function has the same identity. So these top two are known as the even-odd identities that match exactly what we have with the regular sine and cosine functions. Now the next row, these are similar but slightly different from the Pythagorean identities we have with sine and cosine. Right, we're all familiar, cosine squared plus sine squared equals 1. But notice with the hyperbolic version, it's slightly different. It's actually cosine squared minus, instead of plus, sine squared equals 1. Similar over here, this is very similar with the regular trig functions. It's 1 plus tangent squared equals secant squared. Here we've got a minus instead of a plus for the hyperbolic version. And then these two identities are the addition formulas. So if you remember from trig, you had a formula for sine of a sum, and then it gave you some expression like this. And you also had a formula for cosine of a sum. So here we present the hyperbolic versions of those two identities. In this example, we're going to prove two of the identities from the previous slide. These are the two Pythagorean identities that we just saw. So let's start with this first one. Hyperbolic cosine squared minus hyperbolic sine squared equals 1. So we start by taking the left side as it is, and we're going to simplify it until we can show it equals 1. So the first thing we're going to do is replace hyperbolic cosine with its definition in terms of the exponential functions. So when I first, a couple slides back, I gave you the formula for hyperbolic cosine, and this was it. But then it's squared, so we need to put a square on the outside. And then we also replace hyperbolic sine with its formula in terms of the exponential functions, and then that one's also squared. The next step, we're going to square out each of these terms. So in the numerator, we'll use FOIL. So first will be e to the x times e to the x. Well, you add the exponents in that case, so that's e to the 2x. Notice when you do the outer terms, so e to the x times e to the negative x. When you add the exponents, that's 0, so e to the 0 is 1. So the outer term is 1, plus, and when you do the inner term, it's the same product, so you get plus 1. Those combine together to plus 2. And then the last is e to the negative x times e to the negative x. Adding the exponents, we get e to the negative 2x. And then the denominator is also squared, so it becomes 4. Then we have this minus, and then we do the same thing, almost identical, except we have a minus here. And the only difference is this 2 will be negative. Now, notice, because this minus here distributes to all three terms, the e to the 2x will cancel with this minus e to the 2x. I'll circle the next ones in green, so e to the negative 2x will cancel with this one because the minus distributes to that one. And then all that's left are these two in red. 2 and then minus negative 2, that's 2 plus 2, which is 4. So the numerator simplifies to 4. Denominator was already 4, and so we get 1. So notice what we did. We started with this expression, we simplified it, and we got 1, so that proves this identity in part A. In part B, this was the identity we were asked to prove. So the way we're going to get there in a different way this time. We're going to actually start with the identity we proved in part A. We now have established this is true. And we're going to next divide both sides by hyperbolic cosine squared. So on the left, each term in this subtraction, each term will be divided by hyperbolic cosine squared. And so the first term becomes 1, and then we have minus hyperbolic sine squared over hyperbolic cosine squared. And then the right, this 1 also gets divided by hyperbolic cosine squared. Now we just use an identity, right? If you remove the square, if you just look at hyperbolic sine over hyperbolic cosine, that's the definition of hyperbolic tangent. And then the square has been pulled to the outside, so that means it's also squared. And over here, if you pull the square outside the fraction, this is 1 over hyperbolic cosine. Well, that's the definition of hyperbolic secant. And then the square is still there because it was pulled out to the outside. And then we've established this identity. Now we want to determine the derivatives of these hyperbolic functions, hyperbolic trig functions. So let's start with hyperbolic sine. So to find the derivative of hyperbolic sine, we're going to first express hyperbolic sine in terms of its formula that defines it, which I just copied over here, the formulas we saw earlier. So we've replaced hyperbolic sine with this. Now we use derivative rules to take this derivative. Now we see a quotient here, but you don't have to use the quotient rule because the denominator is a constant. Right, you could view that as 1/2 times what's in the numerator. So the 1/2 is just a constant multiple that can be carried along. So here we've carried along the 1/2. Now we still need to take the derivative of what's in the numerator. And because it's a difference, you can just take the derivative of each term individually. So the derivative of e to the x is e to the x. And then we have minus the derivative here is itself times the derivative of the inside part, right? This is a chain rule situation. The derivative of negative x is 1. Right? So maybe I should write this one out over here. When we did the derivative of e to the negative x, it will be itself times negative 1. Now let's put that back in here. There was already a minus in front of the e to the negative x that we didn't have over here. So it's going to be minus what we found here. And the two minuses become a plus. Okay. And then notice what we ended up with is exactly the formula for hyperbolic cosine of x. So we can say this whole thing equals hyperbolic cosine of x. So we just showed that the derivative of hyperbolic sine is equal to hyperbolic cosine. And that matches exactly with what we have with the regular trig functions, right? We know the derivative of sine of x is cosine of x. The derivatives of the other 5 hyperbolic functions could be found in exactly the same way we just did with hyperbolic sine. So we're not going to go through the others, but let's just look at these formulas. So the first one is the one we just derived on the previous slide. Look now at the derivative of hyperbolic cosine. It's equal to hyperbolic sine. That one is almost the same, but not quite, as the regular trig function version. Right, we're all familiar that the derivative of cosine x equals negative sine of x. So this one does not have that negative sign. And then derivative of hyperbolic tangent equals hyperbolic secant squared. That's exactly the same as for the regular tangent function. The derivative of hyperbolic cosecant is negative hyperbolic cosecant, hyperbolic cotangent. The derivative of hyperbolic secant is negative hyperbolic secant, hyperbolic tangent. Notice the negative sign here, that's not in the regular trig version. And then the derivative of hyperbolic cotangent equals negative hyperbolic cosecant squared. So we're only going to see the proof for one of these, but we'll just assume all these others have been proven and we can use these formulas now. You don't need to memorize all of these. You also don't need to memorize any of the formulas from this section. The problems you would have on a test would just ask you to use these formulas and I would provide the formulas to you. But but we'll practice now using these formulas. So in this example, we're asked to find a couple of derivatives. The first one, we have hyperbolic sine of 2x cubed. So I've put the formulas for the 6 derivatives over on the right so we can use those as reference. So notice the function we have here is a composite function because it's not a plain x inside the hyperbolic sine. So that means this is a chain rule problem. The inside part is the 2x cubed and the outside function is the hyperbolic sine. So our derivative we could call dy dx equals the derivative of the outer function means the derivative of hyperbolic sine, so we can see over on the right that derivative is hyperbolic cosine. But remember, as always, when you're using the chain rule, it's not x here, it's whatever your inside part is. That's the first factor of the chain rule. Then we multiply by the derivative of the inside part. So the derivative of 2x cubed, that's a simple one, it would be 6x squared. Now this would look better if we moved the 6x squared in front, because otherwise it might be confusing as to whether it's part of what's inside the hyperbolic cosine, and we know it's not inside. So I'm going to write this 6x squared hyperbolic cosine of 2x cubed. Okay, let's go to the second one. Here we have t squared times hyperbolic tangent of t plus 1. So we know we're going to use the formula for the derivative of hyperbolic tangent, but before we do that, we need to start with the product rule, because we have a product of two functions of t. Okay, so f prime of t equals, so we take first times derivative of the second. Let's go ahead and compute that derivative. So this is another chain rule problem because it's not a plain t inside the hyperbolic tangent. So the inside part is t plus 1, the outside part is hyperbolic tangent. So we start with the derivative of the outer function, the hyperbolic tangent, and you can see from the formulas over in the top right of the screen, the derivative of hyperbolic tangent is hyperbolic secant, and then it's still evaluated at the same inside part. That's the first factor of the chain rule. Then we have to multiply by the derivative of the inside part. The inside part is t plus 1, and that derivative is 1 plus 0, which is just 1. So we often wouldn't even write that, but I'll just put it there so you know we thought about it and knew what it was supposed to be. Now remember, we're in the middle of the product rule. We just did first times derivative of the second. So the next step is plus second times derivative of the first. So the derivative of t squared is just 2t. Now that one, just like before, that would look better if we put the 2t in front of the hyperbolic tangent. So let's do a simplification. T squared times hyperbolic secant of t plus 1, and we can leave off this times 1. And then on the second term, plus 2t hyperbolic tangent of t plus 1, and that's our formula. Here's two more functions we want to differentiate. So this first one, we have a square root of a hyperbolic secant function. So as always, when we see a square root and you're wanting to take a derivative, it helps to rewrite the square root as a 1/2 power. So we'll keep the secant function the same and then raise it to the power 1/2. So now the derivative here, we have z as a function of x, so the notation for the derivative is dz dx. Now looking at this formula here, we have a complicated, or not complicated, but we have an expression in terms of x raised to the power 1/2. If that were a plain x, and we had x to the 1/2, it would just be a power function. So this is a composite function. The inside part is what's in the parentheses, and the outside is the power function u to the 1/2. So we know it's a chain rule problem. The outer function is the power function, so we start with the power rule, bring the 1/2 down in front, and reduce the power by 1. And we keep the inside part as it is when we do that. So the new power is 1/2 minus 1, which is negative 1/2. Now the second part of the chain rule is the derivative of the inside part. So the inside part is hyperbolic secant of 4x minus 1. Let's look at this is a composite function also, right, because it's not a plain x inside the hyperbolic secant. So the inside part now is 4x minus 1, and the outer function is hyperbolic secant of u. So we need the formula for hyperbolic secant, which you can see over on the right. Right, so we're doing the derivative of the outside function first, which is hyperbolic secant. And so that's going to be negative hyperbolic secant times hyperbolic tangent. But in both places where there's an x, we have to keep our inside part, which is 4x minus 1. So negative hyperbolic secant times hyperbolic tangent, both evaluated at 4x minus 1. Now let's keep track of where we were. We're doing a chain rule within the chain rule, right? We had the first composite function, the inside part was this whole hyperbolic secant of 4x minus 1. We were using the power rule, so you bring the 1/2 down in front, reduce the power by 1, we did that. Now we're multiplying by the derivative of the inside part. So that's all that's left is the derivative of the inside part. And we've started that. This is another chain rule problem. The part that we've done is the derivative of the outside function. So what's left is to multiply by the derivative of the new inside part, which is 4x minus 1, and the derivative of that is 4. So all that's left is to multiply by that factor 4. So now we've finished everything. We could just simplify it to make it look a little better. Notice we have a 4 here and a 1/2 here. So those can combine to 2. There's also a negative sign. So let's write negative 2 in the front. Now this term here has a negative exponent, so we could move it to the denominator. So what's left in the numerator are these two factors over here. So let's go ahead and write those. And now we have this term in the denominator, so I don't have a lot of space. I'll just do it this way. Over. Now the term in the denominator will be to the positive 1/2, so we could convert that back to a square root. So it'll be square root of this expression. And I think that will be good for our simplification. So there's our final formula for the derivative in this one. Now let's go to number 4. This one is a quotient rule. Now I just wanted to mention this, and some of you may have thought of this before. If you don't like using the quotient rule, because it is a little bit involved, you can always rewrite quotients as products. So if you wanted, we could rewrite this as g of x equals x to the negative 3 times hyperbolic cotangent of x. If you wrote it that way, then you could use the product rule instead of the quotient rule. This works if it's a really complicated fraction where the denominator is really long. You might not want to bother with this. It may not save you much work. But in this case, you could do that. So either way you want to do this is fine. We'll just keep it with the quotient rule just to get some practice with the quotient rule. So, or we can keep like this and use the quotient rule. Okay, so doing that, we have g prime of x equals, we know our new denominator will just be the old denominator squared. Now in the numerator, we take bottom times derivative of the top. Now the derivative of the top, that's just plain hyperbolic cotangent. We don't have to use no chain rule or anything there. So just straight from the formula, if you look at the top right of the screen, derivative of hyperbolic cotangent is negative hyperbolic cosecant squared. So that finishes bottom times derivative of the top. Then we have minus top times derivative of the bottom, which is just 3x squared. Now there's a couple things we could do to make this look nicer. We'll do one step of simplifying. So the denominator is x to the 6th. Now in the numerator, the first term, it would look better to put that negative out in front. So negative x cubed hyperbolic cosecant squared. And then on the second term in the numerator, it would look better to put the 3x squared in front. And that's times hyperbolic cotangent of x. And then we've got our derivative here. Okay, so we did 4 examples where we practiced using some of these formulas here. And you can see that we combine these with the other rules we've learned, right? Just like all of our rules, we've been seeing how they often get combined when you're finding the derivative of a given function. That's where we'll stop for today. So let's summarize what we talked about today. We covered all of section 3.10, which was on linear approximations and differentials. So we started out by defining what linear approximations are, and we saw that it's really nothing new. It's an equation for a tangent line to a curve at a given point, which we've already been doing for a while. We're just giving it a new name here, linear approximation or linearization. And we saw one use of these linearizations is to approximate function values that might be hard to calculate using the actual formula for the function. So instead, you can create a tangent line or a linearization at a nearby point, and then just plug the value into the linear function, which is much easier to calculate. Next, we move to the topic of differentials, and we saw this is describing a situation where you have a function and you start at one x value and you move to a nearby new x value. And we're wanting to measure how much the corresponding y values changed. And we saw you could use the tangent line to approximate this change in the y value. And when you do that, we call that the differential. And we looked at one use of the differential for determining maximum error. And then we started section 311 on the hyperbolic functions. So we first defined the hyperbolic functions. They were all based on formulas involving e to the x and e to the negative x. And we gave them names that are similar to the trig functions. Then we established some identities, and we saw these identities were very similar to corresponding trigonometric identities. And then finally, we looked at the formulas for the derivatives of all 6 of the hyperbolic functions and did some practice using those formulas. So we still have more in section 311, which we'll do next time. And there we're going to look at the inverse of the hyperbolic functions and find their derivatives.